So trig 6.6 part 1 complex to polar and DeMoivre's theorem doesn't have sound. What? How does that happen? So I'm about to play my own video while recording it and do voiceovers like I'm doing right now in order to guess what the heck I was saying the first time I did this video. So I think I should probably play it at a higher speed just to see. I don't know. If I can speed it up to what, let's see, we'll go to 1.5. I mean, it's not like you can hear me on there anyway, so we won't be causing a problem. So we are converting this polar equation to rectangular form. Here, let me scoot it up. This is number 12. Must be a homework question. I don't know. Seems kind of weird that it's multiple choice. Oh, looks like I multiplied both sides by r. Ooh, okay, let me pause the video for that. Okay, so basically I took this entire equation, oops, let me get my annotate on here. Multiply this whole thing by r. And so you get r squared on the left. This term has an r, this term has an r. And hopefully what we're going to see is that this can be replaced, this can be replaced, and this can be replaced, okay? From the things that we talked about, like in section 6.4, I think, your x squared plus y squared, as well as your x and y. Okay, so let's see what happens in the video here now. Might want to clear this off. Okay, come on, play the video. Okay, no, you gotta hit that button first. Okay, I'm gonna have to get this out of the way because there we go. All right, so, doing the same exact thing I was doing before. Oh my goodness. I probably should have just waited. Ooh, look, they replaced the r cosine theta with x and the r sine theta with y. And x squared plus y squared shows up for r squared. This looks like a job for getting everything on one side. Notice how I'm leaving space for the x's. Why did I put an equal sign in there? Oh, yeah, I erased it. Good. That should be a plus sign. Yeah, I'm like, what am I doing? Okay, so everything basically just got shoved over to one side. So for those of you that are working at home on this, you would be pushing this to this side and this to this side. We just happen to put that there with some space because we're going to be completing the square for the x's and some space for the y's so we can complete the square for the y's. All right, let's see what happens now. Now I'm going to do my little b squared minus 4ac thing that I've talked about before when we complete the square. Should be doing that momentarily. I don't know when we're going to do that. Add b squared over 4a. That's right, we're going to do that. Yes, I know some of you did b over 2 quantity squared back in your Algebra 2 days, which is fantastic. For now, you could use that. But I would suggest b squared over 4a because eventually the a values are going to change when we get to the next chapter. And if you don't know how to incorporate the a's, you make a mistake. It will be a problem. So we completed the square for the x's and got 16. So I added 16 to both sides. And we completed the square for the y's and we got 4. So we added 4 to both sides. Whatever you add to one side, you must also add to the other. Now I'm going to factor this thing after I give myself some space. Yep, that's going to factor, and so is the y's as well. That's something times something squared. It's x minus 4. Could you take half of that middle value when it's -8? You take half of that middle value, and that's what goes inside the parentheses. And over there, then you do y plus 2 quantity squared. And of course, then it equals 20, which is a circle, by the way. That is a circle with a radius of radical 20. Is this another homework question that I cannot read? Okay, there we go. It's getting better. Rectangular coins, P of 1, -1. Why does it keep moving? Oh, yeah, snip it. That'll be fine. Okay, we got 1, -1. Draw it out. Yeah, that's good. 1 to the right, 1 down. That is quadrant 4. Yeah. Okay, so we got a little right triangle there with sides of 1 and -1. And the angle on the inside is, well, if we do the inverse tan, are we going to do inverse tan? Is he going to do inverse tan? Oh, okay, he just went straight to the 45 degrees. Well, that's true. Looks like they want the answer in radians, which would be pi over 4. So they're doing it looks like I'm doing 2 different ways to do this. One, you rotate around till you're facing quadrant 2 and then walk backwards. That's a negative radius. Okay, so we could rotate around to 3 pi over 4. Yeah, and then walk backwards, which would be negative radical 2. I don't know if I'm going to do Pythagorean theorem here in a second, or if we all know our 45/45/90 is got a hypotenuse of radical 2 times the leg. What am I doing? It seems like I'm taking forever to get radical 2. Come on, you can do this. All right, square root, where's my annotate? I don't know what's going on here. Yeah, radical 1 squared plus 1 squared equals radical 2. Okay, so finally negative radical 2 shows up. And then go all the way around. There we go. 7 pi over 4, right? All the way around facing quadrant. So now you're facing this way, which is 7 pi over 4. And you walk forward radical 2, so that's a positive radius. Positive radical 2. Remember in class I talked about naming things. One, I will give you, I'll say, name it 2 other ways, that kind of thing. And we kind of came up with the idea that you would either add or subtract pi, or if you're in degree, 180 degrees. Okie dokie. Let's move on. This is boring. Okay, got another one here. And I'm going to have to clear this off. Transform the equation. Okay. R secant theta equals 3. Come on. Ooh, look at that. We're going to multiply by R on both sides. I don't see how this is helping. Well, okay, because we can cross multiply. Yeah, that would work. Yeah, we're going to cross multiply and get 3x squared plus y squared equals 3x. Okay, all right, we're cross multiplying. And then we're going to bring the 3x over. And that's going to give us x squared minus 3x. Make him change it to minus 3x. Please. Please change it to minus 3x. Why did he put positive? Well, he better figure this out soon, because it's a minus. Anyway, do a little b squared over 4a. That gives me 9/4. The y's don't need to be completed because they already are perfect. How do I know when something needs to be completed? It's when there's a linear x. When you have a linear x term, like that one, that's how you know. I wonder if he's ever going to get the minus figured out. Yeah, folks, that's supposed to be a minus. Maybe he'll figure it out soon. Still hasn't figured it out. Cut it in half. Yeah, that's true. 3 divided by 2 is 3/2. Man. Why did he not figure this out? Is he gonna change it? Yes! Changed it. That's right, folks. It's a minus. Oh, man. Whew, makes me feel better. Okay, cool. All right, let's go on to another one. Come on. Are these just homework help questions? When am I going to get to the 6-6 stuff? Oh, they're graphing. So pi over 3, that rotates you into towards quadrant 1. But then you're walking backwards 1 unit, so that's going to throw you down into quadrant 3. Yeah? Oh, yeah, that would be choice B. Right. All right, this is taking too long. Come on. Aha! DeMoivre's theorem and the nth roots. All right, so we've got something called the complex plane. And that complex plane, which would be a great name for an airline, don't you think? You know, the complex plane. Anyway, we have something going on here. We've got, I don't know if you've ever noticed this, but way back in the day, when you were given a number line, maybe middle school, elementary, it was 0, 1, 2, 3, -1, -2, -3. What they never told you was there was another axis running through here called the imaginary axis. We had the real axis, which is what you were used to putting dots on, and then the imaginary axis comes along. Well, it was there the whole time. Okay. So how do I find 2 plus 3i? It's really easy, folks. 2 plus 3i. Dang it, there it is. 2 plus 3i. You treat it just like a coordinate. 2 to the right, 3 up. Pay attention to the signs so you know which way to go. Oh, I'm probably going to say all that stuff. We're not going to do the nth roots, so you don't have to worry about those. Come on. Speak faster, Mr. Staley. You're taking too much of the children's time. Oh, come on, Mr. Staley. What is going on? Oh, I'm going to draw a number line? Oh, like they haven't seen that before. Okay, I'm going to skip through that part since we've already talked about it. If you are sitting on the axis, that would be a 0i. 1 plus 0i. That's the same thing as the number 1 that you guys used to draw. They would say graph the number 1, and you put a dot there on the number line. But it was really 1 plus 0i. Ooh, 2 plus I, 2 minus I. Take a look at those. 2 plus I, that's this one right here. 2 minus I, that's this one right here. Those are not called opposites. They are called conjugates. Conjugates. Opposites would be across the origin. In other words, they would be flipped across the x-axis and the y-axis, so to speak. Oh, well, I must be talking still. Better delete that. Okay, plotting complex numbers. Whoa, this looks an awful lot like vectors, except these are just dots. So, complex numbers can be, adding is a piece of cake. Add the x's, add the y's. Man, that sounds like the vector components when we added things together like the plane and the wind. It forms a parallelogram. Wow. You can add complex numbers together and get a different, but they're not really vectors, folks. It's just a dot. They're just trying to illustrate to you that 6.1 from vectors looks an awful lot like 6.6. I mean, really a lot. So this should be real easy, you know. I'm guessing we're going to use Pythagorean theorem. Are you kidding? The Pythagorean theorem's coming? Absolute value, sometimes called modulus, which is the dumbest name ever, but absolute value. Now, absolute value is the distance something is away from zero, right? So absolute value is the distance away from zero. Well, what if we're up here at 2 plus I? How far is that away from 0, 0? Because it's not something like 2. It is the Pythagorean theorem again. 2 squared plus 1 squared. So it's just square root 5. Yes, folks, that's all it is. The absolute value of something is the Pythagorean theorem. It's distance away from 0. Do you worry about the eyes? No, you just worry about the lengths of the sides of the triangle. I got a tickle in my throat and I keep coughing. I don't understand why. Probably not getting enough oxygen in my bloodstream. All right. Let's see now. Let's get back on this video. I probably should delete my drawing before I start drawing something else on there. Come on, Mr. Staley, you're taking too much time. Yeah, I'm going to draw an example. Yep, it's the same thing. Pythagorean theorem. 2 squared plus 3 squared is radical 13. So the absolute value. Oh, I'm also showing you right now that we could do negative 2 minus 3i, which is in quadrant 4 or 3. It would have the exact same length. It's just down in quadrant 3. So what I don't want to see is when I say take the absolute value, lots of kids just want to change the signs. That's not what we do. So don't tell me that the absolute value of this thing right here is 2 plus 3i, because that's wrong. You have to use the Pythagorean theorem. So actually draw it out. Boy, that looks an awful lot like vector components. That A and B are the components, and they're the real and the imaginary portion of a complex number. R cosine theta, R sine theta. Wow, that looks so familiar. But you can see, if I took R cosine theta plus I times R sine theta, and I pull the R out, I think I'm doing the exact same thing. If I pull the R out, that's where I'm going to get the R on the outside, and then cosine theta plus I sine theta. Yeah, they like to put the I in front of the sine of theta just because they don't want people to think that I is a part of the angle. I don't know, it's kind of weird, but that's the way they like to do it. Yeah, they just pull the R out. All right, what's next? Okay, we got some examples here. Okay, so 1 minus radical 3i. So I first want to draw it out so I know which quadrant I'm in. I'm down in quadrant 4. That's a 60-degree angle that we're drawing that's inside here. This is 60. Whoa. Okay, remember we could do tan inverse of radical 3 over 1. Don't worry about the negative. Remember, I told you don't worry about the negative. It's important to know which quadrant it's in. Doing a little Pythagorean theorem here with my, to find my radius, which is obviously going to be square root of 4, which is 2. And then as I show you, inverse tan is going to give me 60 degrees. Or pi over 3. I'm not sure if I'm doing this in degree or radians. Oh, come on. What's he doing? Is he taking his own sweet time? Come on. Let's go here. Tan inverse. All right, I'm speeding this up. This dude is taking forever. Now, why did he come up with 30 degrees? That's wrong. That's wrong. 30 degrees? It's supposed to be 60. Everybody knows that the slope that's bigger than 1 on the unit circle is the 60-degree angle. Radical 3 is bigger than 1. What kind of mistake is this guy making? It must have been Harry did this. I mean, seriously. I could never make this many mistakes. Now, we do see we're down in quadrant 3. So if that angle down there is 60 degrees, if this is down here is 60, and you're coming all the way around, that would be 360 take away 60, or 300. Now, why did he put... You better correct this. This 30-degree crap is not right. It should be 2. Okay, this should be 300. These should be hundreds. I wonder why. I feel like I'm making a big mistake here. Let me pause the video and see if I can figure out what's going on here. If anything, you could use 60. Nah, you wouldn't want to use 300. Like, think about your unit circle. See if I can draw a nice circle here. 300's down here. The x value is a half. So literally, we're already wrong here. It should be 2 times parenthesis 1/2 plus, but the sign of 300, right? Remember, these are hundreds, not, I don't know what I was thinking there. Or Harry. We'll blame it on Harry. That'd be negative radical 3 over 2i. Now, could you distribute that in? Sure. That would be 1 minus radical 3i. Now, why would I want to do that? Use an algebraic method to find the polar form? We already found the polar form. Why am I converting it back? I don't know. Am I just double checking my work? Because that's a huge waste of time. This is, yeah, it's always helpful when you read the problem. There's the polar form right there with 300. And this right here doesn't look correct. 2 cosine 300 plus I sine 300. Okay, let's go to the next example. Hopefully I don't screw that one up. Oh, I put 330. I'm even worse there. Should be 300. Still wrong. Like I said, let's see if we do this one right. Okay, let's see here. We got -3, -4. All right, I like that. That's good. And so a little Pythagorean identity, 9 plus 16, radical 25, also known as 5. Okay, so that's the radius that goes on the front of it. Okay, all right, that's good. We need to figure out the angle, little tangent inverse of opposite over adjacent. So that'd be tangent inverse 5/3, which, using my handy dandy calculator, gives me 59 degrees. So inside here is a 59-degree angle. So when I bring it around, that would be 180 plus 59 degrees, or 239. So I better put, when I do this, it'd be cosine 239 plus I sine 239. That's the final answer to this question. So we're going to see if I do it right. Come on. Oh, I got my wrong angle. Whoa. Why did I do 5/3? It should be 4/3. Boy, I'm even screwing up in my repeat video. Tangent inverse 4/3. That's 53 degrees. So this is 53 degrees. Okay, like 53.1. And then we need to add that to 180. So 180, 53.1. We'll just, yeah, 180 50 plus 180 gives me 233.1. So that should be 233.1. 233.1. Man, I wish I would have caught that mistake. Dang. I'm looking really bad today. Well, at least I did this one right in the video. Yep. Come on, 53.1. Write down your 53.1. Good. Good, 53.1. Why did you put 53.1 in there? It's got to be... That's not the final answer. It should be 233.1. Cross that off and hope to die. This is ridiculous. Oh, my goodness. Cancel. Go back to that. Where was it? I don't want part 1. I want part 2. Hold on for a second. Okay, but that can't be the final answer. 53.1. I mean, I understand 53.1 is what I use from tangent inverse, but clearly in the picture, we're down in quadrant 3. So that's 180, whoops. That's 180 plus 53.1. I'm like lost on why I'm using 53.1 when it should be 233.1 for both of these. I mean, what kind of off day was Harry having that he would mess things up so badly for my students? Oh, my goodness. This is ridiculous. Okay, well, hopefully the audio recorded so you can watch this video. And it's shorter than the other one, so that's good. Hope you have a wonderful evening. And talk to you in class.